Hello and welcome to section 5.3. Today we're going to look at solving trig equations. And before we get started, I want you to keep something in mind. The whole goal when we're solving trig equations is going to be to isolate trig functions and use standard algebraic techniques, whether it be factoring, collecting like terms, squaring something. Just kind of keep those things in mind as you're trying to do these. So let's begin with example 1, and this says to solve 2 times sine x equals 1. The first thing I'm going to do is I'm going to divide both sides by 2 so I get just the sine x piece by itself. So that will give us sine x equals 1/2. Now we're not given a specified domain, so if you think about it, there's 2 points when we look at our unit circle where I'm going to have a positive 1/2 for a sine value. One is going to occur up here in quadrant 1. The other one is going to occur over here in quadrant 2. So the value in quadrant 1 that gives me a positive 1/2 is when x is equal to pi over 6. And in quadrant 2, we have when x is equal to 5 pi over 6. And this would work if we're looking at just from 0 to 2 pi. However, it doesn't restrict my domain. So because sine is a repetitive function, we also must include something that looks like this. And what this means is sine has a period of 2 pi. So every increment of 2 pi is going to put me right back here at pi over 6. So I need to include this because I'm not on a restricted domain. We must also do the same thing over here with the 5 pi over 6. Because if I add some increment of 2 pi to it, it's going to continue to put me back over in this quadrant. Example 2 says sine x minus the square root of 2 equals a negative sine x. Now this is kind of a classic case where we need to combine our like terms. Sine x and sine x are like terms. So if I add sine x to both sides, I end up with 2 sine x over here equals, and subtract the square root of 2 equals 0. Then I'm going to move the square root of 2 over, so I have 2 sine x equals the square root of 2. I'm going to divide by 2, so I have sine x equals the square root of 2 over 2, and sine x equals the square root of 2 over 2 in either the first quadrant, or again it's over in the second quadrant, and that's going to occur when x is equal to pi over 4, or when x is equal to 3 pi over 4. Again, I'm not given a restricted domain, so I'm going to add 2 pi n to both of these. Example 3 says to solve 4 sine squared x minus 3 equals 0. So in this case, I'm going to go kind of in a similar process as to what we've been doing. I'm going to isolate the sine value, or in this case it's sine squared of x. So this will give me sine squared x. I'm going to move this 3 over, and I'm going to divide by this 4. So now I have a squared function and a fraction, so to undo my square, because remember I can really rewrite that as sine x, the quantity squared, equals 3/4. So if I square root both sides, I end up with sine x equals the square root of 3, and the square root of 4 is going to give me 2, so I'm going to write it like that, and I get plus or minus. So if I look at my sketch here, I know sine x equals the square root of 3 over 2 at increments of pi over 3. So to get a positive square root of 3 over 2, this will occur at a positive pi over 3 and a positive 2 pi over 3. But because it's plus or minus, I can also get a negative pi over 3, which is really 5 pi over 3. Or I can have a negative 2 pi over 3. So when we go to solve this, we have x is equal to, and I'm going to start out with a pi over 3. So if I go pi over 3, I notice that pi over 3 and a negative 2 pi over 3 are related to one another because they're only off by an increment of pi n, or an increment of pi. So if I take my pi over 3 and I add pi n to it, I know that I'm going to end up with either this value, or this value, or this value if I add another pi, or this value if I add another pi, and so on. And it doesn't matter if I get a negative value or not, because once I go and I square it here, it's still going to give me a positive number. So this is one solution. My other solution comes from when x equals 2 pi over 3. And again, 2 pi over 3 and a negative pi over 3 are only kind of spread apart by an increment of pi. So here I can add plus pi n, and then these here would be my two solutions. If two or more trig functions are involved, the one thing I want you to keep in mind is we want to collect all of the terms on one side, and you either use unidentity or multiple identities if we have to. So example 4 says sine squared x equals 2 times sine x. So right now I'm going to move this function over to this side, and we end up with sine squared x minus 2 sine x equals 0. I notice each term has a factor of sine in it, so I can factor sine out, and I'm left with sine x minus 2 equals 0. Well, now I have two factors, and from my zero product property, it says I can take each factor, set it equal to 0. So I have sine x equals 0, and I have sine x minus 2 equals 0. Well, I know that sine x equals 0 at either 0, or we can call it 2 pi, doesn't matter, and pi. So if I start out at pi, I notice that pi and 2 pi are only off by an increment of pi. So I can say x equals pi plus pi n, or any increment of pi. Now, technically, we could actually kind of consolidate that, and we could just write it as pi n. Either way, I'll accept it. Now for the other factor, I'm going to add 2. So we have sine x equals 2. And when you look at your unit circle, there is no point on your unit circle where sine x equals 2, because at most it's going to equal is 1 or negative 1. So for this one, we say that the solution does not exist. So the only solution we have is this one right here. Example 5 says to find all solutions of 2 sine squared x minus 3 sine x plus 1 on the interval from 0 to 2 pi. Well, this right here is nothing more than a quadratic function. I have a squared term, an x term, and a constant. So I should be able, or I'm going to try to factor this. So factors of 2 are going to be 2 and just sine. And factors of 1 are going to be 1 and 1. I see that because of this right here, one is positive, one is negative, and because I have a plus sign here, I know that both of these are negative. So now, in order to find all my solutions, I'm going to take each factor and set it equal to 0. So I end up with 2 times the sine of x minus 1 equals 0, and sine x minus 1 equals 0. So I'm going to solve for each case. So I end up with sine x equals 1/2 and sine x equals 1. Now the difference between this problem and the previous ones is we are on a closed interval. I'm looking from 0 to 2 pi, but remember this parentheses means I do not include 2 pi, and this bracket means I do include 0. So when I'm looking from 0 to 2 pi, sine x is going to equal 1/2. This is kind of like that first example. When x is equal to pi over 6 or 5 pi over 6. And this is going to be in quadrant 1 or quadrant 2. Then sine x is going to equal 1 when x is equal to pi over 2. And because I'm only looking for a positive 1 on sine, I do not include the value of 3 pi over 2. So this here would be my only solution for that. Number 6 says to solve 3 times the secant squared of x minus 2 times the tangent squared of x minus 4. Well, if you recall from section 5.2, we said that if you mix the trig functions, we should probably convert them over in terms of one trig function. So I'm actually going to convert this trig function here. So I have 3 times 1 plus the tangent squared of x minus 2 tan squared x minus 4 equals 0. When I distribute, I have 3 plus 3 tan squared x minus 2 tan squared x minus 4 equals 0. I'm going to collect my like terms, and I see that we have, from these two, we have tan squared x, and 3 minus 4 is going to be minus 1 equals 0. So next, I have tan squared x equals 1. So if I square root both sides, I get the tangent of x equals plus or minus 1. And this is going to occur at any increment of pi over 4. So if we look at our unit circle, we have pi over 4 and a negative, 5 pi over 4. And these will give us our positive values. And again, these are only off by an increment of pi. So I can say that x is equal to pi over 4 plus pi n, or x is equal to, this is going to give me a negative pi over 4 when I'm here at 3 pi over 4, and 3 pi over 4 and 7 pi over 4 are off by an increment of pi, so then I can add an increment of pi n to this as well. Example 7 says, to find all solutions of sine x plus 1 equals cosine x on the interval from 0 to 2 pi. Well, this problem here is a little bit more difficult. Because I don't have a sine squared or cosine squared, I can't write the function in terms of one trig function versus the other. So the only thing I can do is I could square each side so that I can convert over to one trig function. Now because I'm squaring both sides, it's not really changing anything. So when I do that, I end up with sine squared x plus 2 sine x plus 1 is equal to cosine squared x. Well, cosine squared x, I know I can change to 1 minus sine squared x, and that's going to equal sine squared x plus 2 sine x plus 1. When I move everything over, I end up with, I'm going to add the sine squared, so I have 2 sine squared x, which takes care of that term, plus 2 sine x. When I add, or I'm sorry, I'm going to subtract this one from this one, which is going to give me 0. So now I can factor, it looks like, a 2 and a sine x out, and I'm left with sine x plus 1 equals 0. Now I can use my zero product property and set 2 sine x equal to 0. When I divide by 2, I'm left with sine x equals 0. And because I'm looking at the domain from 0 to 2 pi, I know that sine x equals 0 when x equals, oops, sorry about that. So when x equals 0, because remember I include 0 but not 2 pi, so this is one solution. Then I'm going to take my other factor, sine x plus 1 equals 0, or I get sine x equals a negative 1. Well, this occurs when x is equal to 3 pi over 2. So these are my two solutions. And one thing I would like to caution you on is remember that when you are squaring a function, sometimes it will produce extraneous solutions when you go to solve. So we need to make sure that we double check our work. Example 8 says to find all solutions of the sine of 2x minus the square root of 3 over 2 equals 0. So first thing we're going to do is we're going to add that square root of 3 over 2. So we are left with sine of 2x equals the square root of 3 over 2. And because this is what we call a multiple angle, because you have a 2x right here, we're going to have to solve this just a little bit different. The first thing you're going to have to do is you're going to have to think of the big picture. When does sine x equal the square root of 3 over 2? And this is going to occur at increments of pi over 3. So we know x is going to equal pi over 3, or x is going to equal 2 pi over 3. Now, I have to plug, whenever I solve for x, I have to take that value and plug it in up here into my original function. So now I really need to take this 2x here and set it equal to that pi over 3. So I'm going to say 2x equals pi over 3, and I'm going to solve. So I end up with x equals pi over 6. And likewise, I'm going to do the same thing over here. I have 2x equals 2 pi over 3, which is going to give me x equals 2 pi over 6, which is really pi over 3. And because we were not on a restricted domain, I'm going to also include plus my pi n. And actually you would do 2 pi n, but you're dividing by 2 from right here. Same thing with over here. So I'm going to go plus pi n as well. Example 9 says to find all solutions of the tangent of x divided by 2 minus 1 equals 0. So I'm going to first start out by saying tan of x divided by 2 equals 1. Well, I know tangent equals a positive 1 at pi over 4 or 5 pi over 4. So I'm going to take this x divided by 2 set it equal to pi over 4, and solve for x. So I'm going to multiply both sides by 2, and this tells me that x equals pi over 2. And if you double check your work, if I plug pi over 2 in for x, I have pi over 2 divided by 2, which is pi over 4. Tangent of pi over 4 is really 1. Now, this up here really would have been plus pi n, because these are separated by an increment of pi, but because I divided that by 2, I multiplied that by 2, I'm really going to add plus 2 pi n to that. So that will accommodate both of these angles. And our last example for today says to find all solutions of 4 tan squared x plus 5 tan x minus 6 equals 0. So again, I'm going to sit there and I'm going to look at this and say it looks like a quadratic function. So you can either use quadratic formula or you can factor. And in this case, it will factor. It's going to factor out into 4 times the tangent of x minus 3 times the tangent of x plus 2, and this is going to equal 0. Then I'm going to solve each factor. So we have 4 tan x minus 3 equals 0, and tan x equals a negative 2. And I'm sorry, I kind of jumped ahead. Tan x plus 2 equals 0, and I just subtracted the 2. So I'm going to do the same thing over here. I'm going to get tan x by itself. So tan x equals 3/4. And this isn't a nice trig number, so the only thing I can do to solve this is I can take the inverse. So I can say x equals the inverse tangent or arc tangent of 3/4, and then I'm going to add pi n to it. Likewise, negative 2 isn't a nice number for tangent, so I'm going to have to say x here is equal to the arc tangent of a negative 2 plus pi n as well. So my two solutions are right here. And because we've been doing so much trig, I happened to run across this picture and I thought it was kind of cute. So on that note, enjoy your fun fact, and I will see you guys in class tomorrow. Have a good day.